Introducing William C. Meyer, Space Projects Division, Sandia Corporation.
The phenomenology of a nuclear explosion is well known. Generally, more than 50% of the energy of an explosion is delivered in the form of soft X-rays. Smaller amounts are delivered in the form of other radiations, usually about 1% in the form of neutrons and about 0.3% in the form of gamma rays. Most of the rest of the energy is carried away by the kinetic energy of the bomb debris. When a nuclear event occurs near the Earth's atmosphere, almost all the energies of the X-rays, gamma rays, and neutrons is absorbed by the atmosphere and re-emitted as light, heat, and the kinetic energy of a shock wave. There is no atmosphere associated with the detonation in space, however. The X-rays, gamma rays, and neutrons radiate in a 4-pi inverse square geometry. Scientists from the Los Alamos Scientific Laboratory estimate that the X-rays from a 10-kiloton explosion can be detected from as far away as 200 million miles. This distance is equal to the diameter of the Earth's orbit around the Sun. Gamma and neutron detectors can be used to provide additional information at lesser distances. If space were clean, that is a true void, the detection capability for a nuclear event by a series of detectors would be predictable. However, space is not clean. There are solar X-rays and solar winds consisting of protons and electrons. There are cosmic particles and gamma rays. The Van Allen belts could be another possible source of background radiation. There may be even other radiations that we do not know anything about today. To evaluate the effects of these backgrounds, it was decided to build a system of X-ray, gamma ray, and neutron detectors and their associated logical decision circuitry, which could be used to measure a nuclear event. It might be said that the signal is known, and the purpose of the present Vela program is to evaluate the background noise.
Groundwork for the design and development and static and flight testing of the detection system was started early in 1961. Representatives of the Advanced Research Projects Agency, Los Alamos Scientific Laboratory, Sandia Corporation, Space Systems Division, and other scientific and contractor groups assembled to define areas of responsibility. Careful consideration was given to such items as launch vehicle, life expectancy, reliability, telemetry requirements, types of detectors, and logic circuits. This film will detail the work of Sandia Corporation in designing and arranging for the manufacture of logic circuitry, which was compatible with the Los Alamos detectors. The logic circuitry, essentially an airborne computer, analyzed the millions of bits of information from X-ray, gamma ray, and neutron detectors and translated the data into a simple data frame of 256 bits per second, which could be handled by narrow bandpass telemetry links. 10 X-ray detectors, designed and built by Los Alamos, were uniformly spaced over the surface of the satellite. 6 to 8 detectors would look in a single direction at one time, which provided a high order of coincidence for a plane wave signal. Shielding of the photomultiplier tubes from the direct rays of the sun was accomplished by placing a thin skin of beryllium over the fluor. Integrated into each X-ray counter was a guard counter. The counters were used to identify charged particles produced within the satellite by cosmic rays. Stray particles generated within the satellite had to pass through a guard counter before activating the X-ray detector. To determine which X-ray counters were illuminated by the sun sensors were appropriately placed on the edges of the X-ray detectors. The Vela detection satellite also contains 6 gamma ray detectors. These units were evenly spaced around the satellite, but underneath its thin skin. Each detector was a solid plastic fluor about 2 by 3 inches, mounted on a photomultiplier tube. The neutron detector system consisted of 2 helium-3 detectors surrounded by 10 pounds of polyethylene. These units, like the gamma ray detectors, were located under the exterior surface of the satellite. The overall logic system may be broken into 4 major subsystems: the X-ray coincidence, gamma ray coincidence, steady state, and data handling circuits. The primary detection criteria consists of a multiple coincidence of short pulses from the 10 X-ray or 6 gamma ray detectors. At the time of an X-ray or gamma-ray coincidence, an analysis of outputs from many detectors is made to determine what radiations might have caused the coincidence. There are a total of 10 X-ray detectors placed on 10 of the 12 points of the icosahedron. Since X-rays of interest cannot pass through the structure of the satellite, a total of only 6 to 8 detectors can see a particular signal. The output of each X-ray detector photomultiplier tube is fed to a coincidence-determining network. This network delivers an output for each 3-fold, 4-fold, 5-fold, or 6-fold coincidence, and chooses for transmission to the ground information from the most significant event. This event is the first highest-order coincidence occurring in a given time period. The information transmitted for the most significant event is an X-ray pulse height for each X-ray detector, a gamma-ray pulse height for each gamma-ray detector, whether particle detectors associated with each X-ray detector were fired, whether each X-ray detector was in the sun or shade, and the time of the event to the nearest 16 milliseconds. Although data from only the first highest-order coincidence is stored, the total number of 3-fold, 4-fold, 5-fold, and 6-fold or more events are counted. The gamma-ray circuits are similar in operation with a few minor exceptions. Since gamma rays can penetrate the structure of the spacecraft, the 6 detectors are uniformly positioned inside. Also, the coincidence-determining network generates pulses only when 4-fold or 5-fold or 6-fold coincidences are received. Less information is required at a gamma-ray coincidence. Only gamma-ray pulse height analysis for each gamma-ray detector, a particle detector analysis, and the time are needed. The X-ray and gamma-ray coincidence circuits comprise the major portions of the measuring system. However, some additional steady-state measurements are made. Singles counts from each X-ray, gamma-ray, and particle detector provide a state of health indication as well as general background environmental information. For determining high-intensity steady-state background radiation, a measurement of each detector's anode current is provided. Single pulses from the neutron detector are counted, providing an additional detection capability. A few measurements concerning the state of health of the satellite, consisting of temperatures, voltages, command position, and timing signals, are included. The data handling system accepts the information from the X-ray, gamma-ray, and steady-state systems and stores this information in a binary format of 256 bits per frame. Sequencing circuits within the system allow this stored information to be read out at a rate of 1 frame per second, which can be handled by the telemetry link. In addition, there is a 30,000-bit magnetic core storage. Data from an 8-hour period can be stored and read back to the ground station on command, thus reducing the time required for ground station operation. Design criteria included reliability, power consumption, weight, volume, and cost. Considerable effort was made to ensure that reliable components were used and that circuit designs were checked for operation over wide temperature and voltage ranges. Active and inactive system redundancy was included in critical areas. Reliability studies were made in an effort to determine if the 6-month minimum life in orbit requirement was being met. In some cases where the original design was inadequate, redesign was accomplished for desired orbit time. The final design of the detection logic system, as conceived by Sandia engineers, comprised over 20,000 parts, including 2,500 transistors and 3,500 diodes. Consultation between the layout engineer and manufacturing development personnel resulted in a more simplified and reliable module. This check and recheck of design also often led to the solution of problems which might have delayed production and cost thousands of dollars. A high degree of reliability in the production of the various modules was provided by several manufacturing techniques. Various methods of module box manufacture were tried, such as welding, extruding, and casting, but none proved to be satisfactory. The solution lay in milling the boxes from a solid block of aluminum, which provided the necessary strength and the close tolerance required for module placement. Another technique involved the use of plated through circuit board holes, which allowed solder to flow through the holes and adhere to both sides of the joint. Sectioning techniques combined with microphotography allowed the supplier to verify conformance to specifications. Visual inspection of sample modules by quality assurance engineers gave the manufacturer and Sandia Corporation a prediction of the reliability of the complete run. Using powerful stereoscopic microscopes, such items as board dimension, component placement, solder joints, and protective coating were checked. All modules were tested on Sandia-designed PT-1207 testers under extreme temperature environments. Each sample circuit module was checked against a detailed quality assurance inspection procedure. If the piece parts passed this rigid inspection, they were shipped to Sandia for assembly. The complexity and quantity of testing required to flight qualify individual module boxes and complete payload systems made it necessary to design a fast automatic checkout system. A commercial computer and high-speed readout unit were utilized in conjunction with Sandia-designed computer circuits, signal generators, and data display units. The computer was capable of giving complex electrical problems to the system under test, decoding the answers sent back, and determining if they were the expected answers. If the system was operating as expected, a new problem was given, and so on, until the system was completely checked out. As many as 30,000 checks per minute could be given. If, however, the system failed to perform properly, the computer stopped, printed out the expected and observed answer, and waited for instruction from the test engineer. Additional logic system reliability tests were run with the satellite and logic system placed in a special temperature chamber. The system was checked over a temperature range of minus 25 degrees Fahrenheit to plus 165 degrees Fahrenheit, with the electrical supply voltage being varied plus or minus 15% from normal. The environmental test facilities of Sandia were utilized in evaluating the effects of high-intensity noise levels that would be experienced at booster injection rocket firing, the problem of electrical arc over at near zero pressure levels, and the effects of handling and explosive bolt firing during separation and nose fairing ejection. While these environmental tests were going on, the scientists and engineers of Los Alamos Scientific Laboratory assembled and checked the detectors, sensors, and guard counters. These components were then shipped to Sandia for integration into the payload. As the various detectors and counters were mounted and cabled into the system, a final check was given to the payload before shipment to Space Technology Laboratories in California. At STL, the two payloads were given further environmental tests after they had been integrated with the STL portions of the spacecraft. These tests further verified the design of the system and ensured success of the program. System checks were simulated using a computer and readout equipment. The first dual satellite launch took place in the fall of 1963. The launching vehicle lifted the two satellites into a parking orbit. The booster then placed the two satellites into an elliptical orbit with a 50,000-mile apogee and a 200-mile perigee. When the two satellites were at their apogee, one was injected into a 50,000-mile circular orbit. After one more pass through the transfer ellipse, the other satellite was also placed into a 50,000-mile circular orbit. The two satellites had a nominal separation of approximately 140 degrees. Thousands of miles away in Sunnyvale, California, scientists and engineers awaited the first indications from the two satellites. Information from the tracking and receiving stations at New Boston, Kaina Point, Seychelles Island, and Vandenberg Air Force Base were sent to STC to permit analysis of the condition of the satellite and experiments. The STC display console was provided with sufficient information to describe time and position for firing the injection motor, the orbit achieved, perigee location, and other vital information. Data received from the tracking stations was recorded on magnetic tape. This tape was returned to Sandia Corporation in Albuquerque for reduction and analysis using high-speed computers. In the past few minutes, you have seen some of the activities involved in designing, manufacturing, and testing the first satellite nuclear detection system. Although this system is functioning with a high degree of reliability and furnishing valuable data, the program does not stop at this point. Plans call for a series of advanced airborne detectors and logic systems to be placed into orbit. These systems will be used to continually improve our nation's ability to detect nuclear bursts in deep space.
Carried away by the kinetic energy of the bomb debris. When a nuclear event occurs near the Earth's atmosphere, almost all the energies of the X-rays, gamma rays, and neutrons is absorbed by the atmosphere and re-emitted as light, heat, and the kinetic energy of a shock wave. There is no atmosphere associated with the detonation in space, however. The X-rays, gamma rays, and neutrons radiate in a 4-pi inverse square geometry. Scientists from the Los Alamos Scientific Laboratory estimate that the X-rays from a 10-kiloton explosion can be detected from as far away as 200 million miles. This distance is equal to the diameter of the Earth's orbit around the Sun. Gamma and neutron detectors can be used to provide additional information at lesser distances. If space were clean, that is a true void, the detection capability for a nuclear event by a series of detectors would be predictable. However,
introducing William C. Meyer, Space Projects Division, Sandia Corporation.
The phenomenology of a nuclear explosion is well known. Generally, more than 50% of the energy of an explosion is delivered in the form of soft X-rays. Smaller amounts are delivered in the form of other radiations, usually about 1% in the form of neutrons and about 0.3% in the form of gamma rays. Most of the rest of the energy is... It might be said that the signal is known, and the purpose of the present Vela program is to evaluate the background noise.
Groundwork for the design and development and static and flight testing of the detection system was started early in 1961. Representatives of the Advanced Research Projects Agency, Los Alamos Scientific Laboratory, Sandia Corporation, Space Systems Division, and other scientific and...
Space is not clean. There are solar X-rays and solar winds consisting of protons and electrons. There are cosmic particles and gamma rays. The Van Allen belts could be another possible source of background radiation. There may be even other radiations that we do not know anything about today. To evaluate the effects of these backgrounds, it was decided to build a system of X-ray, gamma ray, and neutron detectors and their associated logical decision circuitry, which could be used to measure a nuclear event.